Hello student. So today we will continue our second unit. Okay. In last unit we will discuss the two important terminology regarding magnetism, which is magnetic field intensity or magnetic induction and magnetic flux. So today we will discuss the important properties of magnetic field. Okay. So, in last lecture, we have discussed that the magnetic field vector B is completely different from that of electric field vector E. Okay. So, the first important properties of magnetic field is if we take the line integral of magnetic field around any closed path, okay, then the line integral of magnetic field around any closed path will be equals to mu naught times the current through the wire bounded by the closed path. Okay, or we can say the line integral of magnetic field around any closed path is directly proportional to the current through the wire bounded by the closed path. So line integral of B dot dl is equal to mu naught I, and if you see carefully, then it is nothing but this statement of Ampere's circular law. Okay, so now we'll prove this statement, prove this property of this magnetic field. So for this, let us consider a long straight wire carrying current I through this. Okay, this we have considered. This is a long straight conductor through which I current is passing through. Okay, the magnetic field around the conductor is in the form of concentric circle. This we already know. Okay, this is given by right hand thumb rule. Okay, if we put our thumb in the direction of the current through the conductor, then the direction of our fingers will tells about the direction of magnetic field lines. Okay, so the magnetic field lines will form these concentric circles acting in the plane of paper. Okay, now take a closed path at a distance r from the current carrying conductor. Say we have considered this circular path. Okay, and so for which is at a distance r from the conductor. Okay, and on this path we have considered at any point a dl. Okay, a small point element dl. Okay, and at this dl the direction of B will be in this direction, because the tangent at any point will give the direction of magnetic field B. Okay, so this is how we can represent this. The magnitude of the magnetic field at a distance r from the conductor is given by, this is again a standard result which we used as it is. We can derive this relation, but here we use this result as it is. Okay, this you have already done in your 10 plus 2. Okay, you can cross check there. Okay, the magnetic field at a distance r from the conductor is given by mu 0 times current passing through that conductor divided by 2 pi r. Okay, so now if we calculate the line integral of the magnetic field B, okay, for this path which shown in this figure. Okay, so that will be B dot dl will be B dl cos theta. Okay, and theta, you can see the direction of dl and direction of B, they are in same direction, so theta will be 0. So this can be written as integral of B dot dl, and B is what? B is the magnetic field due to the at a distance r from that conductor. Okay, so that will be mu 0 times I 2 pi r dl. Okay, so this can be taken outside because r is fixed and I is the current passing through that conductor, that is also fixed. So this can be taken outside the integral. So what we are left with, integral of dl. Okay, and what will be this? This will be the complete path of this circumference. Okay, so that will be because the circular path, that will be 2 pi r. Okay, so the integral of dl over the closed path will be 2 pi r. So this 2 pi r will get cancelled out. Okay, so what we are left with, the line integral of magnetic field will be equal to mu naught times I okay, where I is the current passing through that conductor, and this is nothing but the Ampere circuital law. So this is how we can prove this property. Okay, but the one of the important property of magnetic field is the line integral of magnetic field around any closed path is directly proportional to the current through the wire bounded by the closed path. Okay, so this is the first important property which we discuss. Okay, the another important property of magnetic field vector B is this: if we take the curl of the magnetic field vector, then it is directly proportional to the current density through the closed surface. That means del cross B will be mu cross mu naught times J, okay, where J is the current density vector. Okay, so to prove this property, let us consider a curve C enclosing, we have considered curve C enclosing a certain region through which various currents are flowing. Okay, as shown in this figure, I1, I2, I3, I4, I5, these various currents are flowing through this region. Okay, the volume current distribution is assumed to be steady. Okay, throughout this volume the current distribution is assumed to be steady, and in such type of current distribution the current density J vary from point to one point to other point. Okay, the J is varying, the current density vary from within that surface from point to point, it gets vary. Okay, so the total current enclosed by the curve C, the total current enclosed by the curve C is the flux or the current density J through the surface enclosed by the curve C. Okay, the direction of area is always normal to the surface given by n cap. Okay, as J is the current density through unit area, therefore the current through ds will be given by this. Okay, the current through small area element ds, that will be J dot ds. Okay, or J dot ds can be written as J dot n cap ds. Therefore the total current through the closed surface given by total current I will be integral of J dot n cap ds. Okay, and as we already know, the line integral of magnetic field will be equal to B dot dl will be equal to mu 0 times I. Okay, so this line integral B dot dl will be equal to mu 0 I is displaced by this value in this equation. So this equation will become this thing, line integral of B dot dl will be mu 0 times surface integral of J dot ds. Okay, now using the Stokes theorem we can write line integral of B is equal to the surface integral of the normal component of B. That means this B dot dl, what we are doing, we are using this Stokes theorem. Okay, the statement of Stokes theorem which relate line integral to the surface integral. Okay, so this will become line integral of B dot dl will be equal to surface integral of curl of B dot ds. Okay, now replace or from this equation 1 and 2 we can write this equation, which is surface integral of curl of B dot ds equal to mu naught times J dot surface integral of J dot ds. Okay, now if you compare both these equations, both sides, what we have surface integral. Okay, and then if both the surface integrals are equal, then there has to be this condition, del cross B, that means curl of B has to be equal to mu naught times J. Okay, so this is our result. Okay, and this is the second property of magnetic field vector B. Okay, and this result is again one of the important equation for electromagnetic theory. Okay, and this equation shows the relationship between magnetic field vector B and the moving charges producing these magnetic fields. Okay, now we'll come to the third property, which is about the divergence of magnetic field vector B, and the divergence of magnetic field vector B is always 0. That means del dot B is 0, where if you remember, del dot E can be written as negative of gradient of a scalar potential V. Okay, but in case of magnetic field, del dot B is 0, and because of that only we have discussed this magnetic field vector B behaves completely different than the electric field vector E. Okay, so the divergence of magnetic field vector B is defined as the magnetic flux per unit volume passing through a surface S enclosing the volume V. Okay, so this is same, if you remember, the same way we have defined this mathematical definition of divergence of E. Now in case of B, it will become del dot B will be limit volume tends to 0, the flux of B through the surface S enclosing the volume V over volume, means flux, the magnetic flux per unit volume passing through the surface S enclosing the volume V. Okay, so the flux will become B dot ds, okay, over the closed surface S. So as the magnetic lines of force are source free, okay, and they do not have any starting or ending point, so therefore the surface integral of the normal component of B over the closed surface is 0. Okay, so B dot ds will be 0. If B dot ds will be 0, that means del dot B will also become 0. Okay, so this we have proved the divergence of magnetic field vector is 0, and this is also known as the Gauss line magnetostatics. Okay, like del dot E, if you remember, we can the electric field vector del dot E is rho by epsilon 0, which is also known as Gauss line electrostatics. Okay, but in this case of magnetic field, del dot B is comes out to be 0, and this statement is also known as Gauss line magnetostatics. Okay, and this Gauss line magnetostatics which states that the net magnetic flux through any closed surface is always 0. Net magnetic flux. Okay, it will be possible only if we consider that free magnetic poles do not exist, or the poles always exist in pair, that is no monopoles exist in nature. Only then this can be possible. Okay, so these are the three major important properties of magnetic field. Okay, and based on these three important properties, we can write the we can discuss the comparison of electric and magnetic fields, which is okay. The electrostatic field, we know the electrostatic fields are conservative in nature, so those fields are known as conservative field. Okay, but magnetic fields are non-conservative nature. Okay, and the electric field lines do not form closed path, they originate from a point and terminate at some other point, but magnetic field lines, they form closed path. Okay, the simplest source is a point charge, and the simplest source for magnetic field lines is a dipole. Okay, there has to be two poles, north pole and south pole. And other properties, the line integral of electric field vector is 0, E dot dl is 0, but the line integral magnetic field vector is mu naught times I, and for electrostatic field del cross E is 0, but for magnetic field lines del cross E is mu times J, and the Gauss line electrostatics is del dot E is rho by epsilon 0, and for magnetic field Gauss law is del dot B is 0. So these are the properties by which we define electric field and magnetic field, and through these properties we can differentiate between electric field and magnetic fields. Thank you.